Hello again. Welcome back to this course on fundamentals of data science. And now we are discussing about k-means clustering. So this is what we have for today's discussion: k-means clustering analysis and other clustering methods. Basically, what we are going to see here is how actually we do this clustering analysis. For example, how can we determine the number of clusters, and what are the challenges in k-means algorithms. Finally, we are going to look into different types of clustering algorithms that are available in hand. So these are some of the ways in which we can actually evaluate the k-means clustering. There are a lot of practical challenges that comes in with such algorithms, and we should be very careful. Is it okay to go by this method if you want to solve certain problems? At times, for certain domain, k-means clustering algorithm is quite good, but for certain data sets and certain applications, it doesn't really fit well. In other words, at least you have to do certain process to modify the actual data from different dimensions, for example. Let's move inside and discuss in detail what is actually happening. So first question that I was telling, cluster defined by center and shape and spread. So we know that that's how the clusters are defined, and in this case, determining the number of clusters in a data set is very important process. As we know that k-means clustering algorithm always clusters these data points with some distinct characteristics or similarities, and then it has a k-centroid. In other words, it creates a k-centroid means, and by means of this k-means, it allocates every data points from the data sets to the nearest centroid. In other words, the nearest Euclidean distance between them, and based on that, it tries to recalculate again and again. But again, the final question is, in this case we have 3 points. How do we determine this 3? Why not 4? So that's one of the intuitive question that people come up with. So again, if you have certain information about the domain, it will really be helpful for you to determine how much clusters, or in other words, how much the k is to start with. Then comes the shape and spread of actual clusters. So for example, you can see here, if you try to update the clusters with different points, at one point it actually converges, and maybe your shapes are not necessarily, say, circular or oval. It may be of different structures. Maybe if you consider this connected points, maybe your thing is like the actual clusters that you have here is something like this, that particular one clusters, and then comes the other one here. I mean, this is after the actual convergence that has happened, and here is another one. Of course, there is one thing you should be aware of, that those points at this point are really at the border. Anyway, that's another issue that people consider in evaluation of this such data sets. Anyway, what I try to say is that these shapes are not necessarily circular or oval. It can be of any shapes, and not necessarily curved. It can be even like square shapes or any other shapes that we might wonder. But the question again, another question comes in, is that how much time does it take to converge, and how does it converge? Like, after a certain data points, how does it converge? So this is the question again. That question has been answered by this slide, determining the number of clusters in a data sets. So the optimal choice of k will strike balance between the maximum compression of the data using single cluster and maximum accuracy by assigning each data points to its own clusters. So that's what it is called an elbow based system, in which we are trying to see the percentage of variance explained by means of this number of clusters. So as we can see here, so k-means must have your data set as such, and then for efficient performance of the system, is it okay to increase the number of k, or is it okay to decrease the number of k? As you increase the number of k, there may be other issues comes along the way. So we have to make sure that we have to converge, make sure that everything is included. In this example, we see here the number of clusters chosen here is at least 4. By adding another cluster does not give much modeling to the data. By adding another cluster, say cluster number 5, doesn't really give us any benefits for our data that us have in hand. So that's why we have to make sure that the number of clusters, number of k points is always optimal when we choose those points. Okay, with this thought, let's understand or try to understand what are the other downsides. We know that one of the downside is choosing the number of clusters. So one way to overcome it is by means of this elbow graph. It shows us that 4 is the optimal cluster for this particular data set. We are trying to calculate the variance, right? In this case, we try to calculate the variance and the percentage of variance explained, and we get almost there more than around 80% there with the 4 clusters, and after that it doesn't make much change. So adding extra cluster doesn't really reveal much. Okay, then is the question of shape and spread. Well, that's very interesting question, because sometimes our data points are spread in a very different way, completely different way. So it's very hard for us to get the actual idea. So that's where the challenge comes in, challenge in identifying the cluster. So you could see here in this figure, it's like 2 circles, the inner circle and the outer circle. So this clustering, it's very hard for us to separate the traditional way. Say for example, you are using the Euclidean distance as one of the measures, and you have taken the k means, and again the question is how many k. In this case, probably you might think, yes, there are 2 circles, then I go for 2 k's, and you are going to have a centroid, and based on the centroid you are going to assign all the data points that are closer to the centroid to those points, and eventually you can see what is happening is that you are actually performing this operation, and then just like this is what happens. The split happens this way. But from the original figure, which is over here, it shows that the inner circle has similar points and the outer circle has similar points. So what are we going to do in this circumstances? So that is one more challenge in identifying the actual clusters. So if you just like this, then that's going to be a mistake. So some people suggested that if this is the case, then you may have to actually model this whole process by means of another transformation. You can transform this circular, 2 circular data sets into a different form, and after which you can actually perform this clustering methods. Maybe just to suggest, say for example you just cut this circle and make it as a spread, say flat. Just my thought, maybe you can think about it. Maybe this is the inner circle and this is the outer circle, and now it's easy to check it out. And then if you like to perform it differently, this is your first transformation, and the second transformation, if you wish, you can still go for the smaller circle here and the bigger circle here. Everything started from the actual data set, but it takes time and effort, and modeling is not that easy. So which means that the given a data set, you spend a lot of time just to perform these process and not for performing the actual clustering. So the question again is, to do these clustering, do I have to perform all these tasks? In most cases, many researchers would say that they are not willing to do all these tasks just for performing clustering. Rather, many people would say that, well, I will better go for another method. Well, it's up to you to decide based on your applications. So this is one example, and let's look at another example and see how we can overcome some challenges. So here again, left hand side you can see this data sets. It's kind of one cup over the other one. On the right hand side, you are trying to use this k-means clustering methods. By means of that, you are actually finding to fit and gather the data points, but you can see what has happened here is that you are actually split this as one cluster, and then here is the other cluster. So the two clusters have been formed, but it's clearly seen that this is a mess, because we in fact have skipped the blue data into half, as well as the red data into half, and we have mixed up these two in this way. So this is one of the limitations. We don't really have to perform clustering methods which are always spherical or always circular, always oval. So that's one of the questions. The spread of data points is a very vital thing. So how does you really perform this operation? Can we able to perform the operation like this? Is it possible to provide a cluster like this and then you come up with a cluster like this? Yes, you can do that. Say for example, you are starting your clustering centroid from this place, and you can always try to include all the data points that are here, and data points are here, which means that you have to a little bit modify the entire process of k-means and the idea of centroid. Your idea of centroid should not focus on the actual spread based on the circle, ovals or sphere. So this spread is comparatively different way of spread as it goes evolved like this. We have to make sure our actual k-means method should be completely modified in a way that it fits your given data. So this is one of the biggest challenge. Though you try to do it originally, as we can see that the k-means, this one tries to find the centroid with the neat sphere, the data around, but it performs very badly initially. So that's why we have to be very cautious in determining how the things would go up in clustering of data points. So this is another important aspect of the whole process. Let's look at one more shape here. How about this shape? So you have this data points here, huge set of data points, and when you perform this clustering methods, it actually spreads like this. So this is one cluster, in fact this one cluster, and then the other one goes here. Looks like everything is fine, right, as you can see here, but if you look closely to the left hand side, these two clusters, there is one small set of data points or here, and often we try to miss it, and even in the after clustering this has not been assigned any of those clusters. So one mistake that we made here is the whole cluster here, which is supposed to be 1, has been split into 2, and this one, which is supposed to be the second cluster, has been completely ignored. So this is one of the problems that we face in such a system. So what are we going to do when we come across such system? Which means that we can go for a new methods of clustering algorithms. So there are different types of clustering algorithms that are available, and let's look at few points here on how we can actually overcome such challenges with different clustering methods. So here is some of the popular clustering methods: the partitioning clustering, density based clustering, distribution model based clustering, hierarchical clustering, fuzzy clustering, then comes the mean shift clustering. Let me briefly tell you what is some of these clustering. We are not going to discuss in detail about all the clustering methods that are available, but some of these methods, if you can look at the word, from the word itself you know what is those type of clustering. So for example, the partitioning clustering, as the word suggests, here the data set is divided into set of K group, or you are going to partition into different groups, just like the cluster center is created and then you are going to distribute according to the distance matrix. It's very similar to typical clustering methods, but we are going to actually use the process of cluster to minimize and compare other centroid by means of partitioning. You are trying to partition different clusters. And then comes the density based clustering, and we can see that sometimes some data points have high densities. So high density data points are connected together or clustered together with certain type, certain any shape. It can be of any shape and arbitrary shapes. So this algorithm does it by identifying different clusters in the data sets and connect the areas of high density into one cluster and dense areas with low density all connected to another clusters. So by means of kind of density features, in other words, it's one of the characteristics of the data that you have, you're going to do this clustering process. Likewise, you have this distribution model based clustering, which can also be done in a similar way. Anyway, right now we are going to look into this clustering method, which is called the hierarchical clustering. So as far as hierarchical cluster is concerned, in data mining and data in statistics, hierarchical clusterings, also called hierarchical clustering algorithm, is a method of clustering analysis which seeks to build hierarchy of clusters. So this uses two different strategies. agglomerative, the first part. This is the bottom up approach. Each observation starts with its own cluster and pairs as the clusters merge and move up in the hierarchy. The next method is divisive, which is a top down approach. All observation starts in one cluster and splits as it performs the recursively. So that's the key idea behind this hierarchical clustering. So with this thought, let's see how it works actually, hierarchical clustering. Here is how it works. So this is the raw data that you have in hand, A, B, C, D, E, F, and with this raw data you are going to use the hierarchical clustering, and you are going to check how this can be done. So B and C are combined together to form another cluster BC. D and E are combined together to form another cluster called DE. Then F is joined with DE to form another cluster. Then BC and DEF are joined together, this and this are joined together to form another cluster. Finally, A joins it as a whole part. This can be viewed in a different setting. For example, you have many clusters So initial step, what you are doing is you are going to have, say, those three are there, and so you are going to combine these two. These two are combined and is sent as there. After which, for example, you are going to combine these two, then you are going to combine these two, then you are going to combine, say, this two. So that is the whole process, like, so you are combining these two, and finally just one whole cluster. It's kind of a hierarchical approach in which people try to go either bottom up or top down approach. So this can be also viewed in a different way. You can see here, for example, you can see P2 and P3 have been combined together. Here you can see P2 and P3 is combined together initially, and it is joined with P1, right? P2, P3 is combined together and joined with P1. So this process here, and again here P5 and P6 combined first, and then it joined with P4. So P5 and P6 are combined together and they are joined with P4, after which we are combining the whole clusters together. Both this setting of P1 and P4 are combined together as a whole. So we do use the Euclidean distance, and also this data set has been combined as a whole from here. So based on this observation, we can actually perform various tasks for such hierarchical clustering. It has a lot of advantages. Unlike a traditional method, we can actually use these methods to overcome some of the challenges that we had in the past. So this is what we had in today's discussion. We talked about the problems that we had in the clustering. For example, determining the number of clusters. Then we discussed about what are the other challenges in k-means clustering. One of the challenges is like as we have mentioned, sometimes we don't know actually what is the spread or shape of the clusters. At times the shapes are quite different for the data set, and it might not be suitable for the k-means clustering to perform its normal task. We also discussed about some of the other clustering algorithms. So that's what we had for in today's discussion, and in the next session we are going to look into the data mining. I am looking forward to see you there in the next session. Until then, goodbye.